All right, so this is my daughter right here. There are no cats yet. This is part 3 of 618. And like one of the outspoken students said on the last day that we saw each other in the exam, I'm aware that I have low energy. So bear with me. I'm going to try to be funny, awkward, whatever distracts you from the stressful situation that is thermodynamics and online teaching and everything else. Um, but I have very low energy. This is why I have Gatorade right here to try to help. So I have a little helper right here. And I'm going to continue now with the examples that we saw. Do you want to help me, Mima?
Okay.
All right. So we were starting the examples, and that was part 2. So now this is part 3. And what we did on the previous part was see the example on the compressor and then started the pump. So now we're going to finish the pump example, and then we're going to look at the heat exchanger, and those notes are posted, okay? So the pump, when we started it, we said that we have water. You're bored already?
Sort of, yes.
All right, what do you think? Are they bored?
Sort of, yes. Because they're not in the class and they have to stay home.
Yeah. They can use a tablet like you. Water enters the pump a saturated liquid and gives you the pressure, and the pressure is increasing, and then this looks like a little bit different from the actual problem statement. Let me take a look. Water enters the pump. Yeah. All right, so we're going to show this on a TV diagram, and we're going to find the specific work required by the pump. So the TV diagram, it's the first thing that I did. It might look scary. You say, I have to do a TV diagram. That's kind of scary. But we know that this is water. It's behaving as a simple compressible system. So we're going to have that equilibrium curve. All right? Yeah? So we're going to start on a saturated liquid. You may remember, because you guys did the video for extra credit, that I didn't grade because not everyone moves on with 100. We're going to start on the left-hand side for saturated liquid. And then we're going to move up because the pressure is increasing. And it tells you that it's increasing at constant density. And density is the inverse of specific volume, which means that it's also increasing at constant specific volume. So it's beautiful, just moves up because it's constant specific volume and because the pressure is increasing. So it's also a vertical line because of the constant specific volume, and up because of the pressure. Right? Bye.
I am not
helping. Oh, you're always helping.
What?
I love you.
I love you too.
Yeah, go use your tablet. It's a great mother moment. No, don't close the door. Use the tablet here. Okay. All right, so TV diagram, not that bad. You could actually do the PV diagram. It would look exactly the same because the pressure is increasing, starting a saturated liquid, and we have constant specific volume. So it's beautiful. Great, okay? Now, to find the work. I mentioned on the previous video that to find it to be specific work, baja el volumen, mi amor, por favor. Baja el volumen. It's going to be H2 minus H1. That's it. Now that I mentioned this, the pump, the work for a pump. ¿Te molesta, mi amor? Bueno, no importa. Mi amor, baja eso un poco. If you look at the online class, that is a folder, I posted some handouts for the future. There are some topics that you're going to cover with Dr. Mikolaitis, such as the diesel cycle, Otto cycle, finishing ideal gases when you talk about entropy, and then a different equation that you're going to see for a reversible or ideal pump. I posted those 4 handouts. Just feel free to take a look whenever you cover those topics. I think those handouts will be useful. Actually, the one for the Otto cycle and the diesel cycle, I started making those when I was his TA. So, circle of life. Yeah, we've been home for a while, so we've been watching Disney Plus. Yeah. Anyway, we need to find H1 and H2. So how do we do that? We need to review that material from before. I need to stop wasting time because it's 15 minutes. And first, we need to know two properties that are intensive and independent. So we know that at 1, we have saturated liquids. So we know that X is equal to 0. The quality, hopefully you remember that. And we know that the pressure is 50 kilopascals. So H will be HF at 50 kilopascals. You can go to your table A5 and find HF. Great, okay? Now H2, how do we find that? We have compressed liquid. I don't know what I did on the notes. I apologize for that. Apparently first I had 100 degrees. So it's compressed liquid. So the properties for compressed liquid were just, like VF at T or UF at T, and now HF at T. So H2 is going to be HF at 85 degrees Celsius, okay? And that we find on table A4. So make sure that you have your tables now. You're practicing this because you're going to keep doing this. And I guarantee that if you are comfortable with the tables up till now, they really don't get any harder. He's going to use the same tables. There's a possibility that he might want to use the tables for refrigerants or other gases. They have the same behaviors as the tables for water and air. It's just that you will need to get them. And I know that the PDF was available. So just make sure you have access to those tables just in case he decides to use them. The behavior is the same, okay? Now we know that we have the specific work, just H2 minus H1. So it's really not that bad. The equation that you see at the very bottom, all right, that says V delta P, that's the equation that we use for a reversible pump, and that's something you'll see later for the Rankine cycle. That's one of the very last topics. So you don't need to worry about that too much. If he brings it up, the reversible pump, that V delta P, you can make a note if you want. Then you can go to those handouts that I posted. You can ask him about it. Like I said, you can interrupt him and say, so far she's only talked to us about delta H, which also applies, and he can explain it. Or you can just talk to me about it, okay? The very last problem is on heat exchangers. Hey, why did I not get organized before? I'm trying to keep this organized because I also have the class for Friday. All right, for the heat exchanger, let me move the class for Friday out of here. All right, for the heat exchanger, if we read it, it says that we have, it looks longer because now we have 2 inlets and 2 exits. Está bien, mi amor?
Yep.
We have 2 inlets and 2 exits. So first it says that we have a saturated mixture of water, and again, this is on the problems that I gave you. A saturated mixture of water with the quality that's given, that's X, enters a heat exchanger. The objective is for the energy of that stream to decrease such that we have saturated liquid at the exit. To accomplish this, we have a separate stream of water flowing on the other side, and it's compressed liquid in the inlet and the exit at 15 and 25 degrees. The mass flow rate of that stream of water that we want its energy to decrease is given 5.56 kilograms per second. And we want to find the mass flow rate required on the other side where the temperature is increasing from 15 to 25. How much water do we need? We know that those are the two values of temperature, and we want to find that in kilograms per second. And then it says additional practice. Find the mass flow rate of the compressed liquid if the temperature is allowed to increase from 15 to 45 as opposed to 15 to 25. And we would need about 100 kilograms per second, which is less than we need if we are controlling the temperature just 10 degrees. We do not want it to increase that much, right, in this case. So we will need more of it, all right, because it will be receiving an amount of energy from the other side. okay? So then the solution is posted, right? I'm gonna go over it until I reach 15 minutes, and after that, you can just look at the rest here. So I drew it as a rectangle, which in reality a heat exchanger is not a rectangle. I invite you to Google heat exchanger from a power plant, and you'll see it's gigantic and elaborate and very different from a rectangle. But this is how we show it in this class. And then we know that we have two separate streams. They're not mixing. Actually, there's a mixer example on the recommended problems. I also invite you to practice that. Solution is posted. And then we have a bunch of values that are given. The first one is that the pressure is 20 kilopascals at the top stream, and that I forgot to include in the problem statement. So let's add that, okay? It's 20 kilopascals and it's constant. It's one of the assumptions for a heat exchanger. The pressure is constant on each side. It's not the same on both sides. It's constant on each side. So the pressure is 20 kilopascals. That's given at the top. It's entering at 0.95, the quality. And then we know m dot 1, which is also m dot 2. We know that 2 is saturated liquid, and that's supposed to be given in the problem. And then we know T3 and T4, and that they're both compressed liquids, and we want to find m dot 3, which is also m dot 4. So if you look at the solution, okay, I start with the equation straight from your supplemental handout. M dot H in, the sum of it, is m dot H out. All the energy in equal to all the energy out. So if I want to expand that using the numbers that I use 1, 2, 3, and 4, I get what you see there, okay? M dot 1 H1 plus M dot 3 H3 equal to everything coming out. Now I can manipulate that equation a little bit to get an expression for M dot 3, all right? So this is important. I know I don't have much time. Again, I need to start with conservation of energy. I write down the equation 1, 3, 2, and 4. Then I say mass flow rate. It's not accumulating on each side because it's steady state. So m dot 1 and m dot 2 are the same. So I can just call that m dot 1 or call that m dot water, whatever is more useful for me. I get that m dot 3 and m dot 4 is the same. I can call that m dot 3. I can call that m dot 4. I can call that m dot a compressed liquid. And then after that, again, all of this is the important part, this one. And then I'm just solving for the unknown over here using the fact that m dots are the same on each side because it's steady state. Now I have m dot 3 in terms of m dot 1 and all the enthalpies. M dot 1 is given, so now I need to find all the values of H. H3 and H4 are the easiest ones to find because it's compressed liquid. So it's just HF at the temperature from table A4. Now H1 and H2. H2 is saturated liquid at the given pressure, which again I forgot to write on the problem statement. So it's HF at the pressure from table A5. Then to solve for H1, because it's a mixture, it will be HF plus X multiplied by HG minus HF. Okay, this equation, which you don't have to memorize with Dr. Mikolaitis, you're still gonna be able to use your notes. Okay, well, we find HF and HG from the table at A5. So we found all the values of H using our knowledge from the tables from before, and then we substitute into m dots, okay, and that's it. We solve for it, and then we see that it's 297 kilograms per second. We need a lot of that cold water if we're not allowing it to increase the temperature that much. It makes sense. Like if you had infinite amounts, you know, like I'm not gonna say the ocean, but you have like a really, really large amount, it wouldn't even increase in temperature. If you have a little bit, temperature will increase a lot because it's receiving this energy from that top stream. Okay, so again, I started with this equation straight from your handout just because I can make all those assumptions that velocity is constant, elevation is constant, no heat transfer between my entire system and the surroundings, no work other than flow work. Okay, this is posted. That's it for today. Thank you for watching and have a great rest of your week till Friday. See you.